Swayam Prabha. Digital India. Educated India.
Description of C1. First, what we will do is that we will compute all these products AWJ. Okay. So first we compute A dot W I for A going from 1 up to n, and how many Wi's we have? I going from 1 to m again. I going from 1 up to m. Okay. So we have n m many products, and what kind of how do we do this? So basically this is just a sigma pi circuit. So we will have a parity gate at the top. Okay, so let's say that I want to compute A dot W I. I will have a parity gate, and I will have how many AND gates? How many? M many AND gates, and each AND gate will take what as input? So what is A dot Wi? It is just the dot product. How do I compute dot product? What will we do here? So basically what is it? It is the product of A1 Wi1, right? So I will have A1 and I will have the bit Wi1 over here, and I keep on doing this, and the last one will take AM Wi M, right? So these products will be 1 if both of them are 1, and finally the parity will be 1 if there is a odd number of such products which are 1. Okay, and that is exactly what we want. So this is a sigma pi circuit where the pi gates have order 2 and the sigma gate has fan-in M. Okay, right. Now, okay, I'll do it over here only. Now I will compute gates DAK for once again A going from 1 up to n and K going from 1 up to m, such that DAK is equal to 1 if and only if XA is equal to 1 and A dot Wi is equal to 0 for all I less than or equal to k. Okay. So I am defining a predicate over here, a predicate DAK. So DAK is equal to 1 if XA is equal to 1 and A dot Wi is equal to 0 for all I up to k, and it is equal to 0 otherwise. Okay. So if one of them is not satisfied, it will be equal to 0. So how can I compute DAK using these outputs now. Should I keep? Okay, let me just preserve this lemma for the time being. So what will DAK take as input? It will take XA and, but how do I do negation? Exactly. So what I will do is that I will just insert a 1. Okay. So I will maybe A dot W1 A dot WK, just 1. Okay. So anyway, A dot Wi has a parity gate at the top. So to that parity gate, I'll just add a extra 1. That's all. So I mean, actually, I don't need to add this layer over here. It is still just a sigma pi. So now with this and at the top, what we get is a pi sigma pi circuit. So this pi still has fan in 2. This sigma actually will now have fan in m plus 1. Okay, because I am adding this extra 1 at the end. And how much is the fan in for this pi? This will also have fan in at most m plus 1, because note that k can go all the way up to m and I have this extra xa. Okay, so this also has fan in m plus 1. Okay. Now, okay. So this is our DAK. Next, we add another layer. So we will compute EK, okay, for k between 1 up to n. No, sorry, for k from 0 to m. Is defined as follows. So EK is equal to 1 if and only if sigma D AK is equal to 0 for A going from 1 up to n. Okay. So look at all the A's. Okay. So for all possible A's, I will look at the parity, how many of those are evaluating to 1. Okay. And if that parity is even, then I will set EK to be 1, otherwise 0. Again, this is easy to see. How do we get EK? So our gate for EK will be a parity gate, which will take as input D1 K up to D N K, and anything else. Now again we have to add an extra 1, because this would evaluate to 1 if there are an odd number of inputs which are 1, but what we want here is an even. Okay. So to take care of that, I will just add a extra 1 over here. Okay. This makes it odd. Okay. So EK will be 1 if there are a even number of DNKs which are evaluating to 0. Okay. So now we, after this, what we get is a sigma pi circuit. Here I have 2, here I will have m plus 1, m plus 1, and here I have n plus 1. Okay. And the last thing is, at the last level I will define C1 of x as equal to 1 if and only if for all k ek is 1. Okay. So, to get this I will have a AND gate which takes as input. So, E actually is for k equal to 0. So, E0 up to EM, and that is the output of C1. Okay. So, this gives me pi sigma pi sigma pi, and so I'll just skip this plus 1. So, this is of the order of something like m n m m and 2, and as I said that if you just apply distributivity over here, you can show that this can be okay, let me just use this space. So, this is pi sigma pi sigma pi m n m m and 2. So, this is will be sigma pi, where this will be something m cube, or no, 1 second. This will be m cube, and this will be n to the power some log. Okay, so you can figure out the constant, but log to less space. One of n, and this pi is n cube. Okay. So, that is just a calculation that you can figure out, but the point is, what is the proof of correctness now? Okay. So, let's see what this thing gives us. Why is this giving what we want? Okay. If OR of x1 through xn equals 0. Okay. So, if OR of x1 up to xn is equal to 0, then we know that all the xi's are 0. If all the xi's are 0, let us look at the circuit. Okay. So, what is each one of these things giving us? What is DAK? What will be the output of DAK? DAK's output will be 0 because each xi is 0. Okay. So, therefore, this first predicate itself is false. Because the first predicate is false, DAK will be 0. If DAK is 0, what will be the value of EK? And note that DAK is 0 for all AKs. Okay. So, this sigma is always 0. So, what will be EK? EK will be 1. Okay. So, for all K's, EK will be 1. If for all K's EK will be 1, if for all K EK is 1, what is the output of C1? C1 is 1 because it is the AND of all the EI's. Okay. So, if OR of x1 to xm is equal to 0, then for all K EK is equal to 1, which implies that C1 of x1 up to xn will be 1. Okay. So, this is actually giving the opposite answer, but that is okay, that is not a problem. I can always add a extra 1 at the end and I can make it the thing. But anyway, that is a minor point. Now, let us look at the other direction. If OR of x1 up to xn is equal to 1. So, if OR of x1 up to xn is equal to 1, then what do we have? We have that there exist S subset of 0 1 to the power m such that S is not empty first of all, and for all I in S xi is 1. Okay, so this is a little bit of abuse of notation. So, when I say I in S, I am looking at the binary representation of I in S. Okay. So, that is essentially okay. So, if OR of xi is equal to 1, I know that there are some indices which are 1. So, S is a non-empty set, and I am looking at exactly those indices which are 1, right. Now, what does Veli and Vazirani give us? So, according to Veli and Vazirani, what it tells us now is that, well, if I look at all these DAKs, what does it tell us? There is some k for which DAK is equal to 1, or so basically, yeah, so for there is some k for which DAK will be equal to 1 for 1A because of this, okay, because A dot Wi will be equal to 0 for all the i's up to k, okay. That will happen with probability 1 by 4, yes, at most probability, at least probability 1 by 4, okay. So, if I is in S, then this, okay. So, by that was theorem 2, by theorem 2, okay. So, by theorem 2, there the probability that there exists a k which is less than m such that, yeah, such that not use this notation, such that DAK is equal to 1 for exactly 1A is at least 1/4, exactly what you said, okay. And now, because of this, what we have is that, well, DAK will be equal to 1. If DAK is equal to 1, then for exactly 1A, which means that this sum will evaluate to 1. If this sum evaluates to 1, then EK is equal to 0, and if even one EK is equal to 0, then this circuit will evaluate to 0, okay. So, which implies that C1 of x1 up to xn, or the probability, not always, the probability that C1 x1 up to xn is equal to 0 is greater than 1/4, okay. So now you see exactly how we are using Bailey and Vazirani, right? We are kind of saying that for exactly 1A, okay, so therefore for exactly 1A, we get this kind of isolation. Okay. And now the rest of it is just fitting things in place. So we have a error of 3/4. So we can, so first of all we have a error in the answer. So we have to flip the answer. So to flip the answer we just add a extra 1. So we define now a circuit C2 . Oh, and one more point is that the circuit C1 that we have currently has depth 5. So, but as I said that using the earlier observation, I can bring it down to depth 2. So, I will define C2 to be a depth 2 circuit. Okay. Such that what does it do? So, it is taking C1 and it has a parity gate at the top and it is taking one more one and it takes R log n many copies of it. Okay. So, this is my C2. Okay. So, therefore, OR of x equal to 0 implies C2 of x is equal to 0 and OR of x equal to 1 implies that the probability that C2 of x will be 1 is greater than 1 minus, or okay, probability that C2x is still 0 is at most 1 over n to the power r. Okay. So, does this complete the lemma? So, we have a uniform. So, it is uniform because we have given the construction family of probabilistic depth 2 circuit. Well, once again you can apply that and you can bring down the depth. So, we have a parity gate and a AND gates only of size n to the power polylog. So, we have shown that it is n to the power polylog. So, even after taking log n copies, the size is still n to the power polylog for us. It is using order log cube and random bits. Okay. So, let us see why is it log cube and random bits. So, initially we had the strings W1 up to Wm which were random. Okay. So, that was log square and random bits. Now, I am adding another r log n random bits. So, therefore, it is log cube and random bits that is computing the OR function with error at most 1 over n to the power r. Okay. So, this proves the theorem. Okay. So, any questions?
You should also have a circuit for computing OR and the top, and like, then it can be sports term.
Huh?
When we just have copy, so we also need to take the OR after that.
Yeah.
Means the OR can be written as a polynomial in using parity at times. Just now there is no output gate.
So, the output will be what? So, output will be 1 second. So,
OR of these.
no, so 1 second, let me see.
Now the OR is over just R log n.
Well, I cannot have a OR gate over here.
No, means write it out as a parity of
Huh.
since the number of parities is like the number of inputs in this OR gate is very few. It's just all R log n.
So what I can do is the following. So instead of putting this 1 over here, the probability that this is making an error is 3/4. So I have probability that all of them, the probability that all of them makes an error is 3/4 to the power or log n. So if I put an AND gate at the top, okay, and I remove all of these, so then I get a probability of error as 1 over n to the power r, and then after that I flip the input using a parity gate in the end. Okay, so then I will have a parity gate which takes this and a 1 as input. That will flip the final answer. Hmm. I mean, because so 3/4 to the power some constant, yeah, I mean see 3/4 to the power r. So if you just keep on multiplying 3/4 with itself, after some constant times r log n, it will come below 1 over n to the power r, right. So 3/4 is a constant that is less than 1. If I multiply it this many times, it will fall below 1 over n to the power r. Yeah, you can call this as r prime to be more precise, some r prime times log n, it will come below, right. Depth 2 because I will have a parity and AND gates. So always we are alternating between parity and AND gate. If I have more than depth 2, I can always apply that note that I had stated earlier and bring it down to only a parity gate at the top and AND gates below it. So you can do that squashing at the end. So you don't have to do it over here. You just build the entire thing and then you do the squashing and then you just make it depth 2. You can bring it down, yeah, you can bring it down, yeah. So from C2 you can maybe go to another C3 and you can bring it down. So that is the beauty of using polynomials over GF2. Okay, so that is the reason why so polynomials over GF2 are used precisely because we can always bring down the depth to 2. But the problem with polynomials over GF2 is with this parity gate, and the way parity gate is handled is by Millian-Fuzzy-Rani. So so this is basically the crux of this entire thing. Okay. Now this is for OR gate. So AND gate is again simple. I am not going to state it. So you can think of it. So you just write it as a corollary. So similarly, AND gate can also be approximated, right. Now actually what have we done? So we have just shown how to approximate a OR gate and how to approximate a AND gate, but now AC0 circuit can have, I mean it has a more complex structure, right. So how do I get a depth, let's say a depth 2 circuit or a depth 3 circuit from AC0? Okay, so now I think I can erase this. So this, I'll just call this as a exercise for you to try. Again, I mean it is just a standard way of applying De Morgan's and doing it, nothing fancy over here. Okay, now what do we want? Yeah, for general circuit. Okay. So we have lemma 3, we call this as lemma 4. So let L be, actually this is also not very difficult, it is quite easy, but let me just state this for the sake of completeness. Let L be accepted by a uniform family of AC0 circuit of depth d, and let R be a constant. Then L is accepted by a uniform family of probabilistic circuits of depth 2 having error at most 1 over n to the power r, size order n to the power log to the power order 1 n, and fan-in order log to the power 4n. Okay. How does this work? So again, the idea is we just do induction on D. Okay. So if D is equal to 1, we have seen the proof. Now assume that it is true for up to D, it is true for D minus 1, and now we have a depth D circuit. Assume that it has AND gate or OR gate, whatever it is, it has a AND gate or OR gate at the top, and below it we have already built up this depth 2 circuit. Now using this earlier construction, we can convert it into a sigma pi circuit of whatever suitable depth, and now again do the squashing and you get a depth 2 circuit. So it's the just the standard thing. Okay. So the only thing that would increase as a result is this fan-in, it goes from log cube n to log to the power 4n. Of course the size will also increase, but that is taken care of by this O1 constant over here. I mean, if you really want to understand this in a better way, try to figure out what these constants will be. Okay. If you actually go through the proof, you can actually compute what that constant will actually be. Okay. So if you compute, you will get what that constant is. The error is the same because I use the same number of I mean I will just keep reusing those random bits for all the gates. Okay. So those gates are anyway different. So whatever random bits I have, I will just reuse them, and yeah, so fan-in log cube n and order log cube n random bits. So this proves it for AC0. Now how to make this deterministic? So to make this deterministic, so what we have now is the following. Okay. So what we have is all these circuits corresponding to the various choices of random string. So this is for, let's say, my random string sum R1. So I have X R1 and so on up to X, R, order log cube n, right? So 2 to the power order log cube n, these many random strings. So I will put a majority gate at the top and I will connect them. So all of them are depth 2 circuits. Now because of this majority, I get a depth 3 circuit. Okay. And now this is a deterministic computation. Okay. And as I said that this does not change the size. So the, okay, of course the fan-in of this is 2 to the power order log cube n, that is okay. And as I said, the size does not change by more than a quasi polynomial factor. So that is still okay. Now there are only two things that are remaining in this entire proof. So we have shown depth 3, but in the original proof, okay, if you look at the first theorem, I had mentioned threshold circuits. Okay, so what are threshold circuits? Threshold circuits will have only majority gates, right? Now what kind of gates does this circuit have? This has majority gates and this has parity gates and AND gates. Now it is easy to see how we can simulate AND gate using majority gate, right? How do you simulate an AND gate using majority gate? You can add constants. So how many constants and what kind of constants will you add? So suppose let us look at it as a simple exercise. So suppose I have n bits, okay, let us say A1 up to AN. Now I want to convert this into a majority. So of course it will take A1 up to AN. Huh? How many more bits? Well, n minus 1 more bits, right? So I will add how many, and what will those bits be? All zeros. This is n minus 1. So only if all of them are ones, then the majority is 1. If even if one of them is 0, then the majority is not 1. So it is easy, and OR gates can also be converted. But now the question is, how do we convert parity gates to majority gate? Okay, so that needs a little bit of a trick. So we'll see that next time. That is not difficult. You can also even think about it, think of how to do it as an exercise, and yeah, so you can think about it. So that is one part, and the other part is of course how do we show Whaley and Vazirani's theorem, okay, so which we assume. So how do we prove that? Okay, so I will stop here.